If you don't know me, my name's Chic, and I'm a member of the West of Scotland area group, MERG membership number 6000. So, to get into this story, we have to start with a little picture of my bench, and there it is there. You can see the multimeter, the oscilloscope, and all the usual suspects, the telephone, calculator, lots of batteries, and so on. But over to the right of that picture, you'll notice the stack. From the bottom to the top, you'll see there's a linear power supply and a switch mode power supply. There's a couple of bench multimeters. There's a counter timer, a Recal counter timer. And right at the top of that stack, there's my signal generator. Now, the signal generator, that's what it looks like, is a wonderful little thing. It's called an FY6800. It's from China, as most things are nowadays. Fairly accurate, as you can see, it's set there to 10 megahertz, and it's got 10.00000. It's close enough for government work. 2 channels, and just to go through the spec of it, it'll go from 1 microhertz to 60 megahertz. Now, just for those that are doing the sums, 1 microhertz is 11.5 days per cycle, so it's a very, very slow waveform. It has 36 preset waveforms, and you can define 64 different user waveforms. I'll give you an output voltage of 10 volts. It'll also include a frequency meter, a counter, an event counter, and a timer, and you can control it via USB from either a PC or a microprocessor. And at the time, it was about £50 delivered from China. I don't know what the price is now. It'll probably be slightly higher because there's been fairly substantial cost of living increases over the past 12 months since this was planned, and over the past 3 or 4 years since I bought the signal generator. Now, those preset waveforms are these: sines, squares, ramps, sawtooths, the Lorentz pulse. ECG is a basic model of a standard sinus pulse for an ECG if you're modelling that sort of equipment. Exponents and logarithms and white noise and modulation, and half wave and full wave rectified signals if you're doing power supplies. Plus, you can define 64 of your own waveforms, which is when this fella really comes into his own. If you run the PC software that you get with it, you can see there's some menus and some buttons to press up at the top, but this main window is divided into 3 tabs. The right-hand most of the 3 tabs is the control window, where you can actually suggest what's going out on channel 1 and channel 2, and if it's modulated by each other, where the sources for the signals are, if it's sweeping, if it's being measured, all manner of stuff in there. If I go to the waveform window, which is the left-hand most tab, I get this. And basically, I can make any arbitrary waveform, and let's face it, that's pretty arbitrary there. Goes from 0, a little bit of noise where I couldn't control my mouse, sweeps up to about 7 volts, and then back down to 0, and then a little lump, and then back up to 7.5 volts, and then down to -5 volts. And it will repeat that waveform over and over and over again at any frequency I want. The waveform can have up to 8,192 discrete steps. So you can do a lot with 8,000 steps. And you can either put it in that way, or you can put it in the text window. The middle tab, there's a text window, which is basically a text editor. And you can copy from Excel or from a program output or whatever, and generate any signal you want in the text window, and this will let you do it. So because you can generate your own signals just by writing them effectively, you end up with hundreds of signals. On my own PC, there's the directories of signals that I've got. I've got PID controller signals, I've got satellite signals and avionics signals and ARINC, which is another avionic standard signal, medical signals, microcontroller pulses, motor vehicle stuff for simulating ignition cycles and faults in the car and stuff like that. And also model railway. And if you look at the model railway directory, there's CAN signals, DCC signals, I2C signals, servo signals. There's also some SPI signals in there. Basically, anything that you want to synthesize, you can do with this signal generator. And it's got two outputs at any one time. So you can also do differential signals, like CAN bus, for example, or dependent signals. If you've got a clock in one channel and the data in another channel, like I2C or SPI, it'll do those as well. So the problem that we had was this: no output, no screen, none of the buttons were illuminated, and no power on the LED. If you notice to the bottom left-hand side of the signal generator, there's a little rubber button with the power symbol on it. And normally when the thing's sitting working, even if it's off, that button's sitting throbbing gently, going from 0 up to red and then back to 0 and then back up to red. Not even that was working. So this thing's completely dead. So let's have a wee look and see what we can find inside it. It's actually surprising. When you open it up, it turns out that the box itself is a standard box that you can actually buy. You know, it's just an enclosure from some manufacturer. And if you go to buy one of these now, you can get them, the same electronics, but in a different box, in a tiny flat box that will take up much less room on your bench. Looking inside it, you can see the back panel there with the power input and some signal inputs. And then there's the Paxilin power board. Paxilin is that brown synthetic resin bonded paper, SRBP board, that power boards are very often made out of. It's cheaper than the FRG4 and it has better characteristics for making power supplies out of. So power supplies very often find themselves made up on these brown boards. So that's the power supply. The green board is the main board, and you can see that at the back there's connections to the front panel. The main great big chip there is an Altera FPGA, 6th generation Altera FPGA, and that does all the thinking. That's all the functionality is built into that FPGA. Moving towards the front of the box, there's a heat sink, and the heat sink's on top of some power op amps, and the power op amps are what drive from the 3.3 volts logic of the FPGA to the plus and minus 10 volts at the outputs. If I look from the other side of the box, you can see there's the switches. I'm now looking from the bottom to the top. There's the power input and the power switch. There's the external inputs. There's the same power supply board, the same main switch. In front of the heatsink, you can now see there's 3 or 4 little red relays for switching outputs, and then the output sockets. And you can now see for the first time the front panel board, which contains the display and the buttons and the beeper and just about all. Now, these things have what's called a healthy hacking community. There's lots of people using them and playing with them and adapting them to their own needs. And they discovered that there was a voltage issue on the earth wire of the BNCs at the front of the device. And so a fix was found whereby one of the earths from the power supply was connected to the earth of the mains. And if you look closely, you can see that there's a multi-strand wire, a little ribbon wire, that goes between the power supply and the main board, and that one of the power supply lines, one of the ground lines, has been cut out and moved over and soldered to the earth of the main socket. So that's already been done on this board. That was done by the manufacturer, it wasn't done by me. It was like that when I got it, apparently, because this is the first time I've opened it. So there's nothing to see, there's no smell of burning, there's nothing looking out of place. So we're going to have to find a strategy to try and fault find this. The fault finding strategy that I started with was to divide and rule. There's three main boards here: the power supply board, the main board, and the front panel board. And so what I'll do is I'll check the inputs and outputs at each of those individually, and that way I'll find which of the three boards I have to fix. And hopefully I'm left with a third of the problem to deal with. There are other possible strategies. Successive division. If I've got something that's in lots and lots and lots of very similar sections, let's say I've got a room with 40 PCs in it and a network connecting them, then what I can do is divide it into two 20s, check the left-hand 20 and see if they're all working, and then check the right-hand 20. There's the fault. And then take the right-hand 20 and divide it into two 10s and find out which of the 10s the fault is in, and keep dividing like that until I find the fault. That's successive division. I can use substitution. I can try taking a board that I suspect and putting a good one in its place and seeing if that fixes the problem, in which case the board that I've just substituted out is faulty. I can do parallel checking. So for example, if I've got a stereo and the left and right channels are ostensibly identical, then I can check the power rails on the left versus the power rails on the right, the input on the left versus the input on the right, the output of the first stage on the left versus the output of the first stage on the right, and go all the way through, checking the good channel versus the bad channel till I find out where the fault is by going past it. At that point, I've walked past it. The good one's still working, the bad one's no longer working, so that's where the fault is. I can check against a known good. So I could try one of these that's known to be good and either substitute or just compare voltages and compare currents and stuff. There's a dozen different strategies for fault finding. But for the time being, I'm going to divide and rule. It's made much easier here by the fact that the outputs of the power supply are the inputs to the main board. And the outputs from the main board are the inputs to the front panel board. So the internal structure of this thing is a sequence of blocks that are in series. The output of each block is the input to the subsequent block. So those, where those arrows are, the outputs of one block to the inputs of the other block, those are going to be crucial. Plus, of course, the input to the power supply board. So that's what I check first, the input to the power supply board. And the mains is okay, check that with a multimeter. The fuse is okay, check that with a continuity checker. The switch is okay, check that with my multimeter again. I then check the output of the power supply board, and those are iffy, in as much as they're not what they should be. So at that point, I abandon my divide and rule strategy and I move on to substitution. I replace the power supply board with my bench supply. As you can see, I've got a bench supply sitting in the stack. So I simply plug the bench supply in place of the power supply board, set up the right voltages and switched it on. And lo and behold, everything works. So that means that I've to isolate the power supply for further investigation. It's the power supply that's wrong here. There's something wrong with that. And that's good news because the power supply doesn't look complicated. And in the worst case, I can either buy or build a very, very simple power supply to supply this. Either buy one for China, make one up, make a linear one up, make a switch mode one up. I've got lots of options here for getting this thing back on the road. Looking at the board, and it looks like every switch mode power supply you've ever seen in your life. Going from left to right, there's two big connectors, con 1 and con 2. Those are the mains input in the switch. And the mains input and the switch are effectively in series. So it doesn't really matter which one's the mains input and which one is the switch, because it'll do the same circuit either road round. And then you've got the common mode choke or inrush choke. Now, we talked about these earlier on when I did the circuit protection presentation a few months ago. Common mode chokes stop inrush current and stop noise from either from the mains getting into the power supply, or more importantly, from the power supply getting out to the mains. And then we have a bridge rectifier, 4 diodes, D1 to D4. C1 is a great big smoothing capacitor. And then we have the chip plus 3 or 4 capacitors and resistors round about that. And then we have the isolation. Now we notice that we have the high voltage to low voltage transformer, which is marked T1 in this board and is vastly overexposed because of my rubbish photography, for which I apologise. Below it, there's CY1, which is a Y-rated capacitor, which is a high voltage capacitor for feedback of signals from the output stage back to the high voltage stage. And down at the bottom there, IC2, which is an opto isolator. And what that is doing is sending back signals from the output again to IC1. IC1 is the chip that's the switch mode regulator. I've got no idea about IC1, so we're going to have a look at that. There's then the 3 windings on the transformer, one for 5 volts, one for plus 12 volts, and one for minus 12 volts. And each of those has got its own single diode rectifier, just a simple half-wave rectifier. And then each of those has got its own smoothing capacitor. The biggest smoothing capacitor will be for the 5-volt line because that's beefier. And if you notice, the diode for the 5-volt line is beefier as well because it's supplying most current. And then at the bottom there, we've got a voltage divider in Q1. I suspect Q1's probably a transistor or maybe an SCR, and that's supplying feedback back to the opto isolator to send back to the chip. Right down the center of the board there, underneath that transformer, I anticipate seeing a gap where all the high voltage stuff is to the left of the board as we're looking at it now, and all the low voltage stuff is to the right of the board as we're looking at it now. And there should be an isolation gap to keep the high voltage stuff and the low voltage stuff separate, to stop the high voltage stuff from destroying the low voltage side. So let's have a look at this chip. It's an RM6203. I've never heard of that. So that's going to be a trip to Google, I'm afraid, to find out what's going on there. But it looks a lot like a lot of these switch mode supply chips. It looks like it's doing the same as lots of others. And just for reference, the voltages that are supposed to come out of this on that socket there are plus 5 volts and plus 5 volts and 2 grounds and plus 12 volts and minus 12 volts from reading the silk screen. As I say, one of the ground pins has been taken away to provide that earth to connect the earth to the mains earth to the circuit earth to stop stray voltages getting onto the BNC connectors. But I'm going to assume that this thing's designed with 2 ground pins there anyway. So I can put the mains back onto it and just put the voltmeter onto these pins and see what I'm getting. I should be getting 5 volts on the 5-volt line. If I have nothing connected to it, I get 5.2 volts, which is a wee bit high. And if I put a load on it, just a resistive load, then it goes down to 3.2 volts, which is low, very low. Similarly, the plus 12 volt line should be plus 12 volts. It says minus 12 volts there, but that's just a mistake when I was making up this slide, mea culpa. When it's off load, I'm getting plus 15 volts, which is way too high. And when it's on load, I'm getting plus 8 volts, which is way too low. And exactly the same with the minus 12 volts. It should be minus 12. And when I'm offload, it's way too high at minus 14. And when it's on, it's way too low at minus 8. So let's have a look at the data sheet. First thing we do is put the chip number into Google. And the first datasheet return that comes up is from one of these all datasheet companies that do nothing but datasheets. And I have to say, I'm a wee bit suspicious of those. I have trust issues with them, so I'm going to leave that one alone. The second one is from bellchip.by. I had to go and look up BY. BY is Belarus, and it turns out that bellchip.by is the semiconductor company in Belarus that make the RM6203 chip. So that is actually the manufacturer's data sheet there. And when I look at the manufacturer's data sheet, it's the same data sheet as the one from the all data sheet company, but I'd much rather get it from the manufacturer. Looking at the circuit diagram, the typical application that comes with it, it's exactly as we just done. Mains in, fuse, inrush current, bridge rectifier, big smoother, the chip with some resistors and capacitors round about it, the big main transformer, the optical isolator, C10 it is there, the 1 nanofarad, that's the flyback feedback capacitor. Now this circuit has only got one output, and it's got 5 volts at 2 amps for the one output, whereas ours has got 3 windings. And then down at the bottom, it's a thyristor in this case to send signals back to the opto isolator. And you can see that there's a gap, an air gap that goes through the opto isolator and up through the transformer and up through that capacitor that keeps the 2 halves of this circuit separate. If that transformer's dead, then so is this circuit, because I can't replace that transformer. But everything else there is just stock jelly bean resistors and capacitors and diodes. So as long as that transformer's good, I'm comfortable that I'll be able to get this circuit working again. If it's not, we'll maybe have to start afresh. So as I say, we went through that in great detail a moment ago. If we turn it over and look at the other side, there's that gap right down below the transformer. Not only have I turned this over, but I've turned it over in the roundabout a horizontal axis so that the mains is still over to the left. And you can see the 2 mains connections in series, so it doesn't matter which one goes to which. There's nothing to see here really. It's all single-sided, lots of copper to let the current capacity work. There's no shorts, there's no bad joints, there's nothing like that. So let's have a final look at the board. And while I'm examining the board, I had an aha moment. And the aha moment I had was over here. Look closely and see if you can see what I saw. C10 is bulging slightly. Every electrolytic capacitor's got a cross stamped on the top of it, and that cross is usually flat, and it's to do with expansion inside, and the one in C10 is bulged. So the cross is less pronounced. And I look closely at it. It's also standing a couple of millimeters off of the circuit board, whereas the rest are all down flush with the board, where they would be if you soldered them. So there's something not right with C10. Now it's going to take 2 seconds to get the soldering iron onto C10 and whip it off and have a look. And there we are. Now look at the slight bulge at the top end of the capacitor. And it says vent on it. It's a venting capacitor. Also, you can see down at where my fingers are, there's the rubber plug has come out, which is bad news. And notice the date code. The date code is 1801. Now that means week 18 of 2001. And that's going to be important because of a wee story that I'm about to tell you. If I take the capacitor and put it down, You can see that the base has also popped out. So this looks like a very sick capacitor. Now let's have a quick check. This is my first line component tester. It lives on the bench at all times, and I can stick anything in it and it will tell me the basics of it. It tests resistors and capacitors and inductors, plus transistors, semiconductors of all kinds, SCRs, MOSFETs, bipolars, diodes, LEDs, everything. It tests them. You can put SMDs on the little pad there in the centre, or you can put leaded components into that ZIF socket. Now, when I bought these, they were £4 or £5 from our friends in China. The last time I looked, they were between £12 and £20. So the price of these has gone up horrendously because of the things that have been going on recently. You'll also notice that mine doesn't have a cover. I made covers for these half a dozen times and gave them away, and I've just stopped doing it, and I just use mine on a base plate. So there's the capacitor. It's put in there, and it says no unknown or damaged part. It's not recognising anything. It just thinks I've put a couple of leads in there. So at this point, out come the big guns, and this is a proper LCR meter. Now this is money, but it will measure, as you can see, it measures 450 nanofarads. Now, 450 nanofarads for a capacitor that is supposed to be 100 microfarads. 450 nanofarads is a 2,000th of what it should be. Right, that should read 100 microfarad. It's reading half a picofarad. It really is nothing, a 2,000th of the value. Also, the other number on there, the 2.98, that's the dispersion coefficient. The dispersion, the ESR, the Q, everything that you could measure for this capacitor said this capacitor's dead. Forget about it. So let's look at some failed electrolytics. There's a catalogue shot of electrolytic capacitors. As you know, these things are voltage sensitive. So there's a minus marking down one side. The minus marking goes to the short lead. The top has got this cross on it to see if it's venting, and there's a rubber plug in the bottom, and that should stay where it is. These are radial components as opposed to axial components. You also get axial ones where there's a wire comes out either end, but they're very, very less common these days. Any electrolytic capacitor you get is going to be like that. Now, I was going to do a great detailed history, starting with Leyden jars and all this good stuff about capacitors at this point, but life's too short and brutal, so we're going to cut to the chase here. Capacitor consists of two plates, metal, separated by something. The metal in between is called the dielectric. There's different dielectrics. You get air, you get oil, you get plastic, you get ceramic, you get paper, you get all manner of stuff. And each dielectric has different characteristics, and they'll give you better or worse capacitance, but they'll also give you other things like temperature resistance or extreme high capacitances or pressure resistance or vacuum resistance or oil resistance or whatever. So picking the dielectric is a science on its own, and that's maybe a whole other conversation for some other Sunday. Most big capacitors use a liquid dielectric, and a liquid dielectric is called an electrolyte. So if it's bigger than a microfarad, then it's going to have a liquid dielectric, and it's going to have an electrolyte, which is a liquid dielectric. And for that reason, it'll be called an electrolytic capacitor. Right? And most of the time, electrolytic capacitors are polarized. They've got a plus and a minus that have to be connected the right way around. There's a whole other conversation to be had there about electrolyte forming and stuff, but that's for another day. Up until the turn of the millennium, the most popular electrolytes were things called polychlorinated biphenyls, or PCBs. There's also EDLC supercaps, which we're not going to discuss here, but they too are They're dry, but they're polarized and they're preformed, and that's for another conversation. It's maybe one for David to do. What happened very much in the 1980s, cassettes and tapes went away, and an awful lot of factories in Japan from companies like Sony and Panasonic and JVC were repurposed to making electrolytic capacitors and cylindrical batteries and things that are basically two pieces of material rolled tightly, because that's what a tape is. But we've got to talk about these PCBs because they're the reason we're here. PCBs are horrible things. They're carcinogens. They will cause a contact rash just by touching them. These things will bite you, they'll hurt you. They are disastrous for the environment. They're not just bad for the environment, they are really, really disastrous for the environment. Not only that, but they'll go straight through a rubber glove. If you've got a PVC, a latex, or a neoprene glove, the sort of gloves that we all use for handling, these things don't care about that. They'll just go through it and bite you. They were banned in most countries in the third quarter or the fourth quarter of the previous century. And then at the turn of the millennium, there was an international convention to outlaw them, and everybody signed up to. So at that point, capacitor manufacturers had to find something else that was safer than PCBs. The PCBs are also called arcolors if you want to come across them. And I know that because I've got a 10-gallon drum in the garage and I've got no way of getting rid of it anymore. They were used, apart from in capacitors, they were used in transformers. You know, the big substation transformer at the end of the street? Those have all been replaced in the past 20 years to get rid of the PCB ones because they were a risk. It was the cooling in those. The great big coils were cooled by being filled with PCBs, and there used to be a big sort of cylindrical header tank of PCB on these at the end of every street, and those all had to be gotten rid of. They're also used in electronics for arc suppression, leak detection. They're hydrophobic, they're soluble in organic liquids, they have an incredibly low vapor pressure, and they were also used as a solvent and a cleaning agent. Now, the dielectric should never get out of the capacitor, but failures, voltage shorts, current shorts, aging, over voltage, over current, overheating. There's half a dozen different ways for a capacitor to be hurt and cause the PCB to get out. So they have to get short of PCBs. And for that reason, the manufacturers started looking to water. And water's okay as a dielectric, pure water. If you just take tap water, it's got so many impurities and free radicals and stuff in it that you can't use that as a dielectric. But if you get pure water, even distilled water, you could just about use that as a dielectric, but it's got a couple of problems. First of all, it freezes. Water, as you know, freezes at 0 degrees Celsius, whereas arcolors, PCBs, tend to freeze at a much, much lower. I think it's minus 80 or minus 100. It's a temperature that you're not going to see in nature. And so for that reason, your capacitors are going to be freeze-proof, traveling in aircraft-proof, whereas water doesn't do that. It also has this thing called hydration, whereby if you put a DC voltage on a capacitor that's got a water dielectric or a water electrolyte, then what will happen is you'll get hydrogen migrating to one plate and hydroxide migrating to the other plate, whereby the water effectively breaks down. And the hydroxide just causes salts to form on the one plate, but the hydrogen will form gas, and the gas will form gas pressure. And that will destroy your capacitor in short order. So for that reason, they had to invent chemicals to add to water to inhibit hydration. So they made very, very complicated organic compounds called hydration inhibitors to stop the hydration happening, stop this water breaking down into hydrogen and hydroxide. And these things were incredibly complicated, but they did have the byproduct that they lowered the open air freezing point. So you made this chemical that you add to water, and you can use water as a dielectric, and this chemical makes the water freeze at a much lower temperature. It increases the dielectric constant, and it stops hydration from happening. So this is the magic bullet, and it took years to get this magic chemical invented. And the company that managed it was a Japanese company called Rubicon, and he left to go to a Chinese company. Now, there's a number of Chinese and Taiwanese companies that are mentioned in this slide, and I'm just going to call them Chinese company and Taiwanese company because I wouldn't insult anybody that's listening to this by trying to pronounce or even to write the names of these companies. They're really, really complex. So Rubicon have got this absolutely great hydration inhibitor, and they're making excellent, first class, really, really good water-based electrolytic capacitors. One of their material scientists leaves Rubicon and is tempted to go to a Chinese company. And he takes the formula with him and develops an identical electrolyte. Chinese companies are not so, shall we say, precious when it comes to intellectual property rights and patents and stuff like that. So the Chinese are suddenly producing millions, billions, trillions of water-based electrolytic capacitors. And then a couple of employees of that company in China go to a Taiwanese company, and they take with them the formula for the magic hydration inhibitor. Except for the formula that they took for the hydration inhibitor didn't include the stabilization components that were added to stop the hydration inhibitor from breaking down. So this Chinese company produces billions, literally, 10 to the 9, 10 to the 12, whatever, of cheap aluminium electrolytic capacitors. But these capacitors don't have these stabilization components, but they do have the hydration inhibitor. So they pass testing. But once you put them in and the stabilization thing isn't there, they eventually degrade. And after about a year or two, hydration sets in and these capacitors start failing. And these were all capacitors that were made between 1999 and 2003. And they started failing between late 2001, 2002. That's why I noticed that my capacitor was made in 2001, because that's a telling point. And between 2002, 2005, most of these capacitors had failed, but there were still problems being reported up to just before the pandemic. We don't know how much this cost. Dell put out a statement saying that dodgy capacitors had cost them nearly $500 million. And you may guess that for every motherboard that Dell make, Apple and HP and Nvidia and Intel and all these other people are doing at least as many. And so there were billions and billions and billions of dollars lost because of these plagued capacitors. And there's now a healthy industry of people recapping electronics. You'll find that any electronics program that you see where somebody takes an old radio or an old television and starts to fix it, the first thing they do is they recap it. They take all the old capacitors and replace them with modern capacitors. Because apart from electrolytics, there are other issues with tantalum capacitors that can explode, and REFA capacitors that have issues with breaking down. Those are another discussion for another day. I'm still talking about this dodgy electrolytic and my little signal generator. So go to the Rapid website, and a decent 1000 microfarad electrolytic capacitor would cost, well, 5 of them for £1.68. So it cost Dell $450 million. It's going to cost me about 30 pence. And actually, it's going to cost me less than that because I had an e-capacitor, an electrolytic in stock that I could just pop in here. I just went into the cupboard in the TARDIS and picked one up and popped it in. The supply that I'm working on, it uses a 10-volt capacitor. It's a 5-volt supply, so a 10-volt capacitor is plenty of overhead. But the capacitor that I had to put in was a 25-volt capacitor, so it's got even more overhead in it. There's a thing called derating in electrolytic capacitors, whereby you should always give a little bit more voltage than you expect to ever see. And the more voltage you can give overhead, the better it is. So 30 pence, or effectively nothing, popped a new capacitor in it. The power supply went back to working as normal. I popped it back into the function generator and it's still working as normal. So lessons learned. Capacitor plague from 20 years ago is still an issue because there are still capacitors for 2001 turning up in equipment. If you open a piece of equipment and you're looking at it and it's dead, always look carefully at electrolytics and tantalums and other dubious capacitors. There are some people that say it's cheaper and easier to just replace these with ones that you know are good than take a chance on them continuing. You've got the thing open, you've got the soldering iron warmed up, and it takes a minute of your life to do it. It's maybe just cheaper and easier to do preventive maintenance like that. And we all get told that we should switch stuff off at the mains because standby mode is wasting power. It turns out that standby mode, apart from wasting a tiny amount of power, is also using the power supply. And the power supply could be wearing out, drying out, heating out, killing power supply components. I'd left this thing on with a wee red light thinking, well, it's not really on, it's just a wee red indicator light. But it turns out that the power supply was on all the time, and years of the power supply just sitting there was enough to kill the power supply. So you should always turn equipment off at the mains. And just as a wee coda to that, in the first week of the new year, my television, which I only switch off using the remote control, so when I switch it off, there's a wee red light on it. My television died. Guess what was wrong with it? Anyway, at this point, I should ask for questions or comments, but since this is now a recorded version of the video, that facility will no longer be available. Thanks for your patience, and if you need to get in touch with me, my email is there. Speak soon.